All right, so let us continue with what we were doing last time. So last time we looked at big O and big omega notations, and here we will look at little o and little omega notations. Okay, so there are two variants. There is a big variant and there is a little variant for both O and omega. And little o, little omega are in fact stronger conditions. So let us see what they mean. So once again, we will start with functions f and g. Once again, we'll start with functions f and g, which are from positive integers to positive real numbers. Okay. And now, what is the meaning of this? So, let us see. We say, so what is the notation? F is equal to little o, okay, small og, if one short way of writing this is that simply in terms of the limit definition that we already know, okay, infinite limit n tending to infinity, f of n by g of n is equal to 0. Is equal to 0. This is what it means. Okay. What is the intuitive meaning of this? When you say as n tends to infinity, f of n by g of n goes to 0, it means f becomes much smaller, insignificant as compared to g eventually, right? As compared to g, f becomes very, 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 very small, and therefore this ratio goes to 0. That is the meaning of this. That is why we say f is little o of g. F is insignificant as compared to g. That is the intuition behind this definition. Okay. And secondly, so we can, well, before I go to the second one, we can write this in an alternative way. What is that? You can expand out the definition of the limit, right? We know how to write the definition of this limit v equal to 0. So anyways, these two are f and g are functions from positive reals to positive integers to positive reals. So there is no need for mod. I mean, you have the mod or you don't have the mod, it's the same thing. So if you expand the definition of the limit, what this says is, that is, for every epsilon greater than 0, there exists an n naught positive integer such that should be mod fn by gn minus 0 actually, but this part is positive. Fn by gn is positive because we are working over functions that go from positive integers to positive reals. So we don't even need the mod. In fact, we can write it in an easier fashion. We simply need to write f of n by g of n minus 0 is anyways not there, is less than epsilon. You take less than epsilon or less than or equal to epsilon, it doesn't really make any difference as far as the definition of the limit is concerned. So let's go to less than or equal to epsilon for all n greater than or equal to n. But what does that mean? This means that is f of n is less than or equal to epsilon times g of n for all n greater than or equal to n. Okay, so this is now in a similar way as we had defined for big O. Right? There we had a constant c which bounds f, but instead of constant we have epsilon which can be as small as we want. Right? So that is the main difference. So what does it mean to say again? What does it mean to say f is little o of g? For every epsilon greater than 0, you can take epsilon to be as small as you want. There is an n naught positive integer such that for all n greater than or equal to n naught, f of n is at most just epsilon times g of n. Right? Now epsilon can be anything, any small number. 1 by n squared, 1 by 2 to the n, 1 by 2 to the 2 to the n. Okay, it can, epsilon goes to 0. That's the correct way to think about it. All right. So that is little o What about little omega? So for a moment, just pause and think about how you defined big O and big omega, right? You defined big O, then you defined big omega, but in a slightly reverse way. And then we had this result that f is big O of g if and only if g is big omega of f, right? That is the same kind of duality that you're going to have here as well. So you will define little omega in a way that finally you will be able to say f is little omega, f is little o of g if and only if g is little omega of f. Okay, so the little o and little omega should also swap. So take a pause, okay, for a couple of minutes. Look at this definition and try to guess what the definition of little omega should be. Just take a pause, 10 seconds. Okay, so what do we need? Well, f should be little omega of g if g is little of f. So essentially, just think about it. It will turn out that this fraction needs to be flipped around. That's all. Okay. So the definition is that we say f is little omega. This is how the notation is. Little omega of g if limit n tending to infinity g of n by f of n is 0. Okay, you can again rewrite this. So I'll write the final thing. That is, you check this. Okay, I'm writing the final thing. For every epsilon greater than 0, there exists n naught positive integer such that what will this turn out to be? This will turn out to be f of n is greater than or equal to epsilon times g of n for all n greater than or equal to n. Oh, sorry. One second. One second. It's one mistake. This will be 1 by epsilon. Is that okay? Is that fine? All right. So let's move on. What do we do now? Let's consider a few examples as before. And we consider the same kind of examples that we have seen before. In fact, what we were seeing last time, we can just consider similar examples. So first one. So let me say 1 is little omega of n. Sorry, little o of n. Last time we showed 1 is big O of n. Now I'm saying 1 is in fact little o of n. How is that? Well, what should you consider the limit, right? So let us check. Limit n tending to infinity, f of n by g of n, that is 1 by n. This is 0, so therefore we are done. Okay. So mind you, when I write proof like this, I'm writing the basic argument, but you have to write it more neatly, okay? Slightly, okay, with proper words. What is the definition? What is the argument? These things you have to write. I'm writing it in short. This is the main idea in this proof. Limit n tending to infinity 1 by n is equal to 0. Okay. The second one, 1 is little over square root n as well. Why do you think? For a similar reason, limit n tending to infinity 1 by square root n is equal to 0. Right? Let me write another example here itself. For example, Square root n is in fact little o of n. Why is that? Well, once again, limit n tending to infinity fn by gn, right? So this time we have to take square root n by n. But that's equal to limit n tending to infinity, again 1 by square root n, that is 0. Correct? Now, can you show that n, so question once again, just as we did last time, is n little o square root n? What do you think? Most probably no, right? Because you are computing this limit and you have already seen what the limit is. Okay, so in fact, in this case, for little o, the proof in this case is much easier. Why? You just have to say the answer is no. And the reason is, well, just look at the limit. Limit n tending to infinity, you have to take n by square root n, right? And that is limit n tending to infinity square root n. But this is infinity, not 0. Okay, therefore, this is not true. So, n is not little o square root n. Is that okay? So that is what this was. And now, last part about little omega. Okay, we have done so many things. So now I'll give you exercise for little omega. The same things that we have seen. Check on your own for the same examples. Okay, not anything more. For the same examples, show that n is in fact little omega 1. Show that square root n is in fact little omega 1. Show that n is in fact little omega square root n, and show that square root n is not little omega n. Is that okay? Should be very easy to check. It's just limits that you have to check. Okay. And now comes the final result, analogous to what we did in the big O and big omega case. So what is the final result? Theorem. Theorem is, so again, let f and g be functions from positive integers to positive reals, right? Then f is equal to little o of g if and only if g is equal to little omega of f. Okay. Let me write down in the more popular notation that we have been writing it. So let me just write f of n is equal to little o g of n if and only if g of n is little omega of f of n. Okay. Now, how do we prove this? Again, this I will leave to you as an exercise because this is much simpler than what we did last time. Just use the definition. It's very, very easy. You will be able to prove this in less than 1 minute. All right, less than 1 minute is what you require to prove this. Let's check this. Okay. All right. So we saw big O, big omega, and we were quite familiar with it. So we moved a little bit faster in this part when we were talking about little o and little omega. I believe as we get familiar with things, we should go a little bit faster. Okay. And now, if there is anything that's not clear, anyways, we'll discuss it, and at that point of time, I can clarify if something is not clear. But the exercises I would really require you to try. Okay, before we meet next time. Okay, so about this discussion, let me conclude this part with a small additional notation. It's called theta notation. theta, and it's written like this, theta. Okay, what is the definition of theta? So let f and g be functions from z plus to r plus. We say again f is equal to theta g or fn is equal to theta g, whatever you like. F is equal to theta g if both big O and big omega hold. F is equal to big O g and F is equal to big omega g. Both of these things should hold. Both of these things should hold. Okay. What does that mean? That is, if you open up the definitions, you need constants, right, in big O and big omega. The main thing is these constants need not be the same. Okay. So there exists a constant C1 greater than 0 and N0, sorry, let me write it as N1 positive integer, as well as constant C2 greater than 0 and N2 positive integer, such that, well, C1 and N1 is for the first thing. So f of n is less than or equal to C1 times g of n for all n greater than or equal to N1. And for the second one, f of n is greater than or equal to C2 g of n for all n greater than or equal to N2. That is what this means, what this definition means, right? But we can do slightly better. Choose, what is a better thing? We'll choose N0 to be the maximum of N1 and N2. Then we have both of these inequalities together. C2 g of n less than or equal to f of n less than or equal to C1 g of n for all n greater than or equal to N0. And in fact, this is enough. Okay, because the other way around, if you have N0 and C1 and C2 satisfying this, then you can always go back. You can choose N1 equal to N2 equal to N1 and get both of these. But if you have both of these, we just saw that you get this. Okay, so these are equivalent. So you can again write down an equivalent condition. Equivalently, f of n is equal to theta g of n if there exist C1, C2 positive numbers and n not positive integer, such that C2 g of n is less than or equal to f of n is less than or equal to C1 g of n for all n greater than or equal to n naught. Is that okay? That is the definition. Shall we look at some examples now? Now, examples are a little more difficult. So, okay, so let's look at examples and some more in the next video. Okay, this I'll stop here. Thanks.